Hello, everyone. Welcome to the second talk in the industrial curriculum of the large-scale structural systems and optimal design, TTA. So I'm the chair, Professor Shelley Zhang, and today we have Dr. Simon Xu to give us a presentation, and I will pass the remaining part, the chairing part, for Patrick.
Okay, thank you. So while Simon is sharing his screen, I will introduce him and then we can start with his talk. So Simon Xu is a tech fellow for vehicle optimization and machine learning at General Motors Advanced Vehicle Development and CEA organization. He chairs the GM Global Optimization Focus Group and is responsible for innovations of optimization machine learning tools in vehicle and electrified propulsion systems development. Simon leads a team of experts focusing on optimization machine learning techniques such as parametric modeling, geometric morphing, topology optimization, generative design, multidisciplinary optimization, predictive and generative AI models. Through his team effort and influence, GM's virtual vehicle development has been continuously improved by the implementation of new tools and processes to meet with the new challenges in CO2, EV architectures, advanced battery design, and electric drive technologies. And so I think this is really interesting for our TTA. And I will give the stage to Simon, and we're looking to your talk.
Great. Thank you. Thank you, Patrick, and thanks, Shirley, and all the organizers. So my name is Simon Xu. I'm going to talk about some optimization and uncertainty analysis from the industry point of view, and we have data that will be hopefully of interest to you guys. So the topic today is stochastic optimization process for robust vehicle performances. And so the agenda goes like this. I have some basic introductions about the challenges in vehicle design, balancing of requirements. And we have spent a lot of effort and accomplished quite a bit in the MDO optimization. And so I'm going to talk about, in addition to that, we are more focused on the variation, uncertainties, quantifications, RBDO. And I'm going to show you a detailed study of a robust optimization and learning from that and future outlook. So some introduction first. So right now, everybody knows the vehicle electrification, fuel economy is a big deal. On top of that, we have federal safety regulations for all vehicles in different markets, not just the US, but Europe and now Asia and China. You want to sell vehicles. So these are primary drivers in the vehicle design, besides the regular performance of accelerations and comfort, quietness, and so forth. So here, I just focus on one problem, which is the fuel economy, efficiency, and EV range requires the significant reduction in vehicle mass, but also while ensuring safety, compliance, and other performances. So this is a very interesting optimization problem that we tackle in the past with manual process, and now we try to move into a more optimization process. So first, I want to introduce the idea of magic of mass compounding. It's just an interesting idea. Some of you may already knew, which is when you reduce the mass in a vehicle, obviously improve fuel economy, right? But also it lowers the loads on the powertrain. Hypothetically, if you're reducing some mass on the vehicle subsystem, like the seats, frames, and the structures, you actually reduce the mass of the total vehicle, which requires a lighter powertrain or smaller battery because you don't have as heavy a system to carry. Now, if you have a lighter battery and powertrain systems, the mass of those systems also significantly reduces, especially the battery. It's very, very heavy. So as a result, you can continue reducing the mass and having improvement, and thus the compounding factors. I don't know if I make it clear. Basically, reducing the mass of some component will result in lower mass in the battery or engines. The battery mass and engine will be actually lower, and as a result, more mass saving can be given, so you can have even lighter engines and lighter batteries. So there's a compounding effect. And also the reverse is true, because a lot of time people don't realize inside the company that we're adding mass just for some convenience in engineering that actually causing cascading effect in mass increase in many other systems. So the same thing can be said in compounding effect for the crashworthiness, which when you protect the vehicle with reinforcement, but if your reinforcement can be made lighter through optimization, that same compounding effect can be affected because the safety mass is actually the loads on its structure itself. So as a result, if you reduce the loads and your safety structure can be lightened even further. So the same idea also holds true. So that's why the mass reduction is a big deal in the finite element world for structure engineers. But it's kind of a very complicated problem to tackle with because you have to satisfy all these other requirements when you reduce mass. So the role of design optimization is that we actually will be able to use the optimization to enable rapid assessment of different ideas and leading to the total optimization for the goal. So typically the objective is to minimize mass because this is a common thing we can use, but there are a lot of performances or we call constraints in the optimization that need to be satisfied. So for example, in safety, you have frontal impact, side impact, rear, offset, rear roof crush, all kinds of scenarios. Each one has its own test cases, many different requirements you have to meet. The two main requirements in the safety is the strength, which is you can think about the safety cage of the vehicle will have to be stiff enough so it doesn't collapse. And so that's the strength part. The other part is the energy absorption, which is not the same in that you want a vehicle to absorb enough energy so vehicle deceleration or the harshness of the impact to the occupant is minimized. So imagine you have to design a vehicle like a spring that absorb energy, but spring is not stiff. So you here right away you have two competing factors that in the vehicle design. So that's the interesting part of optimization. You need to balancing all these factors that sometimes conflict with each other. Also, there's highly nonlinearity in safety design because the strength and energy absorptions affect many different components and there are different parts. So it's a very complicated problem because buckling and path dependencies also existing. So these are the general ideas I'm going to go through really quickly. So reducing mass, simplest way is reducing the materials, like the thickness of the materials. But of course, if you do that, you reduce the strength, so you have to balance the two. Let me go through quickly. So the challenge is that how do we navigate these highly nonlinear systems and also multiple systems we have to navigate with different simulations, all physics-based. And also in manufacturing, we have tolerances, so nothing is built exactly as you need it, as you want it, so that you have to carry some uncertainties in performances. Let me just keep moving. So here's a picture of what we call MDO. I think some of you have been working on this for years and so forth, I've heard about it. It's a multidisciplinary optimization. So it's not a new concept, it's been around for a long time, but the issue is how to resolve it because the complexity of the issue. So you can see in the picture, maybe it's easy to follow. You have different, we call load cases or disciplines. So crash is one thing I already mentioned. You have the front, side, rear, and also you have other requirements such as protecting the pedestrians, so we call it pet pros. Danner is really the bumper requirement, so on and so forth. There's a lot of these. And on the other hand, the vehicle has to withstand noise and vibration. NVH stands for noise, vibration, and harshness. So you have modal frequencies, acoustics, and low frequency, mid frequency, high frequency, different physics. And then you have the dynamics in that the structure has to be stiff enough to set up the suspension system, which has absorbed energies. So you need to have enough stiffness so energy absorption can be made, and also precision of the driving for steering has to be stiff enough so that you can drive the vehicle without actual delay. Then on the other hand, you have fatigue life, durability stresses. So all these kind of interesting things are related to finite element models, basically dynamics models And then you have also the aerodynamics, that some of these has to do with the exterior styling, the architecture, and also in internal aerodynamics in terms of HVAC systems. So all these things have to be considered in the total system in order to optimize. And the reason is that you can optimize one system for some purposes, but the systems are shared among many different disciplines. So you cannot really just change it without affecting everybody else. So that becomes kind of a complicated problem. And so this is where we actually focus on in MDO to solve. So here's basically, you guys can see, right? We actually developed a system called ASPEN, Adaptive Search and Progressive Exploration, as a title. So basically, this is the gist of the algorithm. We could not share too much details because we view this as a competitive edge. So it is the industry-leading algorithms capable of hundreds of variables and hundreds of constraints. So you can solve really large problems in the vast large spaces. And we have still many different commercial softwares that we introduced and academic codes that the Aspen is trying to get to the best of all the possibilities. So we have a system now set up to do this. So on the right, this is the gist of what we do. First, you have an initial DOE, which is in the blue dot, that you occupy the whole spaces. This is 2 dimensions, but actually you have 100 dimensions, then you can imagine that you don't have many points, hardly, in each dimensions in terms of the populating the grids. And then you go through different simulations, safety crash, model analysis, MEH. Then internally, we fit a quick response surface for each of the performances. Let's say if you have 200 performances, then you will fit 200 quick response surfaces. Once you fit that, then you can do optimizations. So that process itself is nothing new or magical. The only issue is that the quick response surfaces for such a sparse and a highly nonlinear space is not very accurate. It's not even close to be accurate. So as a result, you wouldn't be able to just optimize and pick the best from the response surfaces. So we have developed through a lot of trial and errors and different alternatives, find a way to actually go back and basically using the response surface to infer possible high potential area through statistics. And these are the red dots you can see. It's not one dot, it's a dot in one region or a couple dots in 2 different regions or different. So it doesn't really matter. Basic mathematically, we just try to find the high potential areas and populate with a few these red dots, which is additional real simulations. And you can see as we do that, we can actually adaptively zoom into a particular region. And after we've done 20, 30, even 100 iterations, you can get very, very close to the optimum. So even if you have 100 variables, 200 variables, we will be able to solve this problem. So the benefit is that it will demonstrate to the company, we are basically a technology group. We have to justify why we need to spend so much money on high performance computing systems. We have invested, the company agreed that because we will be able to save 100 million costs per year based on the couple million vehicles that we sell each year in the world. So as a result that we have implemented this on HPC. So a couple of things that I want to mention there. Let me see. One of the things that 1, 2, 3, 4. Number 4 is that we also have discrete variables. So a lot of things that easy to do is if you have continuous variable, you can differentiate. This is what we do on the response surfaces. But if you have discrete variables, like you have different grade of steels, you have different material properties. So we actually find a way to actually simulate using continuous function, but actually map or snap it to discrete variables. So you can actually maintain a optimality toward the end. Otherwise, we find actually if you do a continuous, you find basically the optimal solution. But when you snap to the nearest point, it's no longer optimal and the constraint is no longer meeting. So we have to go back, iterate. So that becomes really an issue outside optimization. So now we incorporate the same algorithm, a different algorithm to actually solve the problem using optimization for that discrete optimization problem. Once we find a near optimal, use a continuous. And it's built from ground up for HPC, stand for high performance computing. And also we have different batch of job capability. What that is that when you submit jobs for a safety crash, for example, I don't know if you guys know, it takes, let's say 400 CPUs per job. And it could take 10 hours, 15 hours, depends on the length of the simulation. Whereas for an NVH model, it may take only 2 hours. So if you want to do simultaneous optimization, you have such huge differences in computational requirement. And since we already bought the computer, we want to actually populate the computer with the maximum amount of jobs that 24 hours, 7 days. And so you cannot just leave the computer idle, and IT department is going to give a hard time, say, hey, Simon, you bought this computer, you only use 50% of the time. So we have to make it close to 100%, 90-some%. Otherwise, we'll be in trouble. So over the holidays and things, we have developed a queuing system to maximize the capacity utilization on top of the efficiency of the optimization. So there's a couple of things. I won't get into the detail, just for fun fact. So now we have this powerful tool. I want to show you basically what we do with it. So this is the benchmark. I won't show the people, the company names in case I get into trouble with the company, that we actually did a benchmark. This is a very difficult problem, 145 variables and 146 constraints. The black dot is the convergence rate of the Aspen. So 750 iterations, we can save mass about 15 kilograms, for example, for this system, whereas some of the tools hardly get out of 1 kilograms after many iterations. And who knows when they're going to be converged. I suspect they don't converge to the same answer. Here's another example that we did recently and a similar result. So I can explain in just the next slide why you have such a differences, even though they are all optimization. Somehow I get the computer not liking this slide. I think that one slide has animations. So here is really some interesting thing that you can think about it, maybe come out with some additional research ideas. So a typical variable range, let's say 100 variables, if you have 30 levels, meaning that I have a thickness of 1 millimeter, 1.1, 1.2, 1.3, and usually we will go 1.05. So as a result, you have about 30 levels on typical problem. So that's 30 to the power 100 factorial design possibility. So it's a really, really big space to explore with, let's say, a couple hundred evaluations. So as a result, you need to do adaptive search to get to there. It's like a zooming in 100 times, then you can get to the answer. So that's the only way to do that. So I will just show you the example here. At the bottom, you can see a distribution of blue dots. This is the DOE that we do. It's all Latin hypercube, like Latin hypercube kind of DOE, but we actually have a slightly more optimized version of that. But you can, the original starting point is orange, and lower left is more optimal because mass lower is better, displacement lower is better. You can see actually, even though we are starting design here, which is kind of optimal already by manual standard, when you do a DOE, none of these points are better. You would think the point would be somewhere in the middle, so you can pick the best from the DOE and go from there. That's the kind of a concept people have before they actually know the problem. But the problem is highly nonlinear. You don't get this. That's because the optimality is in such small region. If you get out of it with a DOE, you don't get to that. So say a commercial code that I think that's the biggest software that the EyeSight we've been using for 20 years. It's converging to something that's not quite the optimal, whereas we will be able to find much better solutions in the feasible region. If you look at, this is another problem, it's not the same problem. The reason is that a typical software actually don't want to venture out too far from the original baseline because they get lost in the vast space. So this is a chart that illustrates the point. You have 23 variables. These are the circular chart. And the black lines is indicating initial point, let's say 0. And the inside means lower variables values, and outside means higher variable bar. So basically, you can see the orange ones, they kind of closer to the black line, whereas the Aspen solutions go really try to push inside and even some in cases outside. So it depends on the algorithm you have, how aggressive it is. If you can solve the problem, you might be able to find very, very interesting phenomena inside such a complex, vast regions. And that's why I want to show you, introduce this first before I go to the uncertainty, because that adding the complexity to the problem with variations. So now we kind of solve this problem. We are applying this to any problem that we can see. For example, there's some example here just for fun. So you can see these NVH, these are vibrations, stiffnesses, and dynamics in the middle. That's supposed to be moving, but yeah, I think it can move. This basically the vehicle goes through bumps and so forth. And if you turn attention to the right, it's a different crashworthiness. I just edited the video so that you have the side impact and the rear impact. These are simulating cars hitting from different angles. And you have the car hitting the wall, hitting a pole, and offset means hitting another vehicle at offset locations. And I think dynamic doesn't work, that's fine. And also in terms of design variables, you can change the gauge, which is thicknesses. You have material grades. These are different grades of steels, aluminums, or even magnesiums, or composite. And also you have shape changes, or section changes, and spot welding, because the car is welded by these spot welds with pieces, like basically Lego pieces that put together. And so you zip them in the assembly plant. There's a requirement to make sure the spot weld is minimal mass, so we don't put too many spot welds where we don't need that, but we need those for actually crash performances to make sure that it's tight. So there's also optimization problem that you can solve with these kind of things. So we have been pretty successful in applying these almost everywhere that we could use. So the next frontier is I want to talk about is stochastic and MDO. So now we have a capable process. So I'd like to highlight additional recent fascinating findings we have through our studies on stochastic optimization. So these findings underscore the power of optimization if you have one, and then which can reveal unique insights we couldn't have reached otherwise without the power of the optimization. So with it, a deeper understanding of the complex problems and exploring innovating methods for solving them will be something. That's why I want to bring this example here for people to kind of kick around and maybe ask some questions. And so first of all, we want to develop this on top of the MDO, a stochastic-based optimization methodology to optimize the robustness of the crashworthiness. Because well, in reality, if a car is designed as a 5-star, we think, sometimes the government will randomly take a car from the lot and test it. We may even get 3 stars from that because the variations in multitude of things that could happen and make that kind of deviate. So we want to minimize the chance of this thing happening. And so thus this, we need to have approach. But typically the engineering have an approach, they call safety factors. So basically they over-design it. So GM always, if you look inside, we actually design product with much higher standard than the typical standard that is published. So that's the way it is. But on the other hand, if you do that, you are suboptimal because your mass will be high. Well, your cost will be high. So this is kind of emblematic of GM vehicle. If somebody ever drive a vehicle, it feels heavy, steady, more materials. That's because we have a lot of safety factor building. But I think this is more like a old-fashioned way to do engineering, right? In aerospace, we know that in school. So we want to introduce the process of using stochastic method and variation uncertainty quantification to be able to narrow and maybe design even better, which I'll show as an example, which we can accomplish if we have the right tool. So the benefit of MDSO stochastic is obviously you can achieve fuel economy and also getting a better reliability on your vehicle when you actually have the performance. So these are the typical uncertainties. I didn't list all of them. Material property variations, sheet metal thickness variations, sometimes both, because when you stamp the vehicle parts, because the curvatures and the pressure you're pressed on the die, the metal thickness is not even everywhere. Some places are thicker, sometimes thinner. If you're kneading a dough, you know what we're talking about, right? But also because the pressure and residual stresses, each part actually has a pre-stress or pre-tensions what changes material properties. So that basically all roll into even one part. Imagine you have so many parts together, that's even more complicated. Of course, the operating environment, temperatures, humidity, acceleration off by 0.1 G and make a big difference, speed. And also we have the assembly variations. When you assemble so many parts, each part may be slightly deviate and you end up with big variations. And the last thing is I want to mention there's uncertainties in our simulations because we use like a highly nonlinear simulation like LS Dyna, for example. What we found out actually this kind of explicit solver can exhibit convergence issues. So in the old days, I know that depends on the computer's platform you're running, you may get different results. When I first joined the company, that was kind of an interesting and frustrating fact. So people want only running on particular CPU, particular type of machines, so that they can have a consistent result, even though it's inconsistent between the machines. So they can see, okay, I can adjust it 20% if on this machine all the time. That's the old-fashioned way of doing it. And also, what we found actually, it's getting a lot better. So we have less of a problem, but I still notice, since I handle a lot of models with optimization, sometimes there are some unexplained anomalies in the model. Like I delete a bracket on the lamp in the passenger compartment, somehow the frontal crash performance deviate to what I expected. So there's still these kind of things going on, but I think the engineer kind of managing that, but they don't talk about too much. But the point is there's a lot of uncertainty still in the model today. So reliability-based optimization, reliability-based design optimization, I already mentioned, is that we want to ensure the probability of failure or violation remain low. Like you randomly test the vehicle, it has to pass with a good 5-star rating. We don't want to go to 3-star. Of course, subject to basically all the uncertainties in the design variables, especially in the material property, because we know the steel stock actually has a tolerance they give us. They don't guarantee from the company, the steel company, that they 1 millimeter will be always 1 millimeter. There's a plus minus range and distribution. So if we know that information, we can actually account for it. That's the idea. So this is a simple mathematical formulation. Quickly, you can read that. Basic X is design variable. G is the performance function, such as driven by the variable, could be crash performances. And D is your random variables. But in the problem that I'm going to show, the D is part of the X. Basically, it's the X, but it has a variations when the X is equal to 1 millimeter, the D could be plus minus some small percentages from that. And the PF is the probability of failure, T is the target, because we want the probability be 100%, but it's not possible, maybe 95% target, non-failure, 5% probability of failure, or could be 1%. It depends on the situation. And then, so the optimization really, I have something there. Is really the goal is to minimize the function. In this case, the function could be a mass or cost. That's also important. And subject to the probability of failure be less than some target value. And X has a bracket, lower bound and upper bound, because that's how you do the optimization. So some techniques has been studied, first order reliability method, second order, but I do not quite like these methods, or it doesn't quite apply here because highly nonlinearity, which I get a little bit detail, that we cannot assume the output has a nice distribution, like a normal distribution of it, and it's far from it. So that's why we have to find some alternative ways to handle the reliability and to see if I can move. Just be patient. I press button, you know, move. Oh, okay, moving. So the basic visual image typically have in the literature or people have in their mind is that you have these constraints, multiple requirements, And there is an objective function that going one way, like minimize mass. Of course, as you minimize mass, you're violating the constraints. So the optimal solution, the yellow dot, the yellow-orange dot, is at the boundary when you actually have optimal. Sometimes it's not at the boundary because one constraint is active, the other one may not be active. But assuming that's right at the intersections. So imagine if you do a small basic variations, perturbation of that variables at the optimal values, you will see a cloud around this point. So in order to make it robust, you need to move the cloud away from the boundary, which is a kind of mean shift optimization to get away from it, which is similar to a safety factor we always use in engineering, right? So we know that our target is to be 1, but if we do 1.1, higher is better. And even though there are some variations, I should be able to manage it, sometimes even 2x safety. So it's the same kind of a concept without knowing the complexity of the problem. It usually could work if you have large enough a safety factor. So it's a usable method if you don't have powerful computer or understand the physics. That could work with experience. As you keep moving away, eventually you can get it. So that's what it is. But in reality, how things look, that's another question. That's why I want to show you this example next. So like I said, the limitation is the assumption of normal distribution may not be true. And the real world system, because nonlinear exhibit behavior that do not conform. And when dealing with these systems, we may have difficulties to accurately describe the probability of failure. But like I said, it could be practical that you keep moving from the boundary. Eventually, you can deal with it because we have to deal with it if we don't have any tools to deal with it. So the way to reformulate the RBDO problem, this is not new either, is that you do the same thing, minimize the functions and subject to the probability of failure to be subject. But on this side, the P is evaluated through a Monte Carlo simulation, which is basically you changing the variable around each value based on the tolerances through a distribution and pass the variations through the function to the other end. So whatever come out for that particular constraint is the distribution you're going to get. And if you have multiple functions, multiple output, then the joint probability of that is what we are being interested. Because if you have 2 crash low cases, you want both of them to be highly confident. So maybe one is a value different than the other one. It doesn't really matter. It's really the joint probability of meeting is what we are most care about. So that would be the correct way to solve it, but it's more complicated because now you have to do Monte Carlo simulation for each time you do evaluations, which itself, like I said, each performance assessment takes 10, 15 hours with 400 CPUs. So how many Monte Carlo simulation can you do? So here I don't repeat basically why we need to actually do the Monte Carlo simulation because these issues in nonlinear system. So I want to just give this I just draw without the data is that if your function is monotonic like one on the right, yeah, I think the point and the cloud relationship is more well behaved. It will be in the middle, and you can quantify this approximately with normal distribution. So that's pretty clear. So if your function, typically our function look like this, which is there is a little peak bottom. Let's say lower is better. Mass lower is better, performance, acceleration, lower the better, intrusion, lower the better. And there is a sweet spot. That's what we said. If there is a sweet spot, if that sweet spot is pretty small, when you do Monte Carlo simulation around those peak values or bottom values, you will probably get something at the bottom. This is the schematic. You have to do the simulation to see what it is. I have some examples in the end. Your point actually could be in the boundary, and people don't realize that or don't understand that. So we have engineers talk about this. So the way to think about it is pretty simple, is that if you have a value here, anything that's not this value will be worse than this. So that's basically what this cloud was telling you, that that point is the best and everything else is worse. So when you shift the whole cloud, and this point is not in the middle, so you have to re-quantify. Plus, it's not a circle. It could be something ellipse. at a minimum. It could be much more complicated than that. So this is really the background that we have to go in to understand the actual problem complexity and how do we solve it. So here, basically, I have some distribution. I already mentioned one on the left. On the right is another problem. I won't get into the detail what the problem is because it's hard to kind of get permission to show all the engineering applications on product design. Basically, this is another one you can see. We have a baseline design. If we do a DOE, the DOE actually is above the baseline, which is worse. And that's typically, and there may be one or two. So basically, if the problem is easy, then you will see there's a lot of points below the baseline. You just pick that one and optimize your way. But in reality, the optimization is extremely difficult. So you do not expect anything like this, such an easy task to go over. Of course, this one there's some lower, but the force is too high. So this is not necessarily better than a black dot. So that's why it makes harder or make it interesting to solve it with optimization. So Monte Carlo simulations, that's simple. Basically, you just do a Monte Carlo simulation with random and then using response surfaces, because that's something we already built, and we can use this to as a surrogate model. Even though response surface may not be that accurate, but at least give you around the point, very close to it, the accuracy is good enough for assessment. But then we can update the surfaces locally once we get to be closer to the optimal. So there's two different ways. SORA sequential optimization. So some people have done is that they do a deterministic optimization first and follow up with reliability assessment and try to adjust around that. So this could work, but like I mentioned, this will make your design kind of very close to the design that you already have. And the ideal way is to do sequential, instead of sequential, concurrent optimization. So you want to actually, there's a lot of work here. Basically, you want to actually do the optimization, assess the reliability at the same time for each of the points you're getting, and then you fit response surfaces, and then using Monte Carlo simulations on each of the points to get the distributions of the variability. And then I would go fit another response surfaces for the entire domain, so that now not only know the performance of whichever the functional value is at which point, but also the variability of that particular S values, which is input. So another way to say that is that if I have an input at a certain value that's optimal, I will know whether its performance is good, whether its reliability is good. If I have another point that's alternative, I will know this. Now I have two response surfaces of the entire field for each performances that will give you both information. So if I can define a problem like this, then I can solve it, because now I just have two different requirements for each requirement that originally, and just double amount of a constraint. Since I mentioned that our algorithm does not really have a problem with a lot of constraints, double the amount of constraint is just adding more response surfaces. We can fit these response surface parallel in the HPC, high performance computing, then off we go. So this is how I construct this problem to be solved. So let's find out how do we do. So here we have a safety problem, crashworthiness. I have two variables, not variable, two locases. Each locate has a multiple output, US NCAP and Euro NCAP. And these, one is the car hitting a rigid wall. The other one, the car hitting another car, which is deformable, but at offset. So these are two competing requirements in that if you hit a rigid wall, you want the car to be compliant, because the harder it is, the harder to yourself. If it's a rigid, if it's a deformable barrier, you want a car to be stiff, because you want to, if you are overcoming the other car, and so you sustain less damage. But they want you to meet both so that you balance out yourself and damage to other vehicles. So these are two competing requirements, and we have different requirements for targets. And in this case, it's a reduced problem, so we can study more detail. 28 variables, and there's upper bound, lower bound for each variables that's defined, and also based on manufacturing limitations. Plus, we have a thickness variation distributions based on the plant given variations that they typically have from manufacturing. And so we also define the band around those materials. So the total mass of all parts is to be minimized because mass equal to cost and mass equal to total vehicle performance efficiencies. And these initial performance is close to requirement, but not quite, because that's the best they can do at the time. For that particular low cases, they keep improving. They can no longer improve it. They give us to optimize. So it's not quite meeting performance, but it's not too far away. So we did two optimizations. One is deterministic. That's a typical MDO. We say that we want just minimize mass, subject to meeting all the performance, which was not meeting at first, and see how much mass can we get out of it, but also meeting performance. So it's already a hard problem. Second, we did the stochastic optimization, which, like I mentioned, the formulation that I had before is that I want to increase the probability of both of these performance meeting in the intersections, a joint probability to be as high as possible without sacrificing mass. So that's the problem description. I'll skip that. Same thing, and there's a formulation there, basically minimize E of mass and variation of mass, which we don't need to worry about. The probability of the joint probability of all the crash performances, 1 through I. In this case, I have 4 or 5 different performances. So I want to actually solve this problem with the system that we have in place. So for the deterministic problem, I'll go through this quickly. We do the model preparation, parameterize everything, extract the data, and construct the DOE, run MDO, and then using Kriging response surfaces and optimize on the surface, but we don't trust the result. So we actually select different candidates to go back and iterate and repeat. Like I said, it could be repeat 100 times or even more through the HPC. Basically, we don't need to worry about it, just do it by itself. The stochastic process, the blue ones, is basically adding additional things like Monte Carlo simulation on the response surfaces every time I have a DOE point. So let's say I have a DOE starting with a 100 point distributed throughout. Then I fit the response surface. Now I have a surrogate model. I right away can do Monte Carlo simulation for each of these 100 points around it using the distribution. And now I will know the variability of each of these points, and then I can fit a second response surfaces to approximate the second order effect, which is what is variabilities of each performances at each point, and fit it throughout, and then I have a continuous surface that's differentiable. So as a result, I have 2 different performances. One is the actual performance, the other one is variations of that performance that I can use as constraint to optimize. So that's the gist of it. I will go to the detail that I already talked about it. You can imagine. So this is really the problem. You can see this is what's called an offset barrier. So imagine a car hitting another car with some deformation, and it will rotate and do a lot of things. So it's highly nonlinear. And so here, this is the table. I just hide out all the variables and say I have this amount of variables, lower bound 0 to 100 normalized, and the baseline is sitting somewhere in the middle. None of these baseline is right on the edge, which is not a good optimization problem. Right in the middle, sometimes 10%, 60%, somewhere in between. So the goal is to optimize vehicle first. So here is the first look at the problem. Here we have 2 performance, 2 axes, performance 1, these are not x's, these are y's. Performance 1 and 2, we want to make it better for both. There's more than 2, but we just look at 2. And so the starting point is a red dot. We did a Monte Carlo simulation. I believe there's 500 dots there. And you can see it's a pretty wide distribution. But that's reality. That's what the material that we're given has this kind of variations. So you can see the initial result, the best engineered result is not quite inside the box, which is a feasibility for both, but it's not too far away. And the performances of the variations, the cloud is not even close to be in the box, almost 0, basically, feasible. So that's what we are given. And you can see this shape of the cloud looks like an ellipse, but not quite, but it has a rotational effect. So it's not simple, a circle around it. And the center of the circle is not the initial point. So this is what I mentioned earlier, that's kind of interesting. that we see that. And also some of the points are a little better, but the point is that the points that's better is not to say better because the mass could be a lot higher because we have another objective, which is minimize its mass. So this is what the optimization need to do to fix it. So we actually did the optimization. You can see right away, we improved a lot. So we use this powerful tool I mentioned. And in this case, we have a mean shift. And the reason is, I won't get into too detail, is that we actually have a requirement that's higher than the normal requirement. So if you hit that requirement, there's a good chance that you already are kind of over-designed for robustness. And this is what we see. So if we have to try to move the cloud into, move the blue dot, which is optimal, according to our requirement, then you have 80% chance of meeting the probability of success, which is not bad. Otherwise, we'll not be in business, because if we have 0 chance of meeting, our car is not going to be cut it. So you can see that it's already better. But the other thing you notice that the spread is a lot bigger with the optimal solution. So actually, this is something when I first started in the company, I was working on optimization. The engineer said, I don't trust optimization. Because every time you optimize something, you make things worse, because I'm on the knife edge, on the cliff. And I don't want to fall off the cliff by you optimizing me to the end. So this is kind of emblematic what they have in mind, that you make it optimal, but not necessarily more robust. They cannot articulate that fact, but this is what they're afraid of. But basically our answer is that if you want something fixed, just tell us. We can put a constraint on it. In this case, we didn't have any constraint on the robustness because complexity or something. But if we put it, we may have a different picture. So I want to show you the next result. So this is actually the optimization we did after we introduced the robustness variations into. And you can see it's a lot tighter. And it's almost 100%, 99.4. So we're pretty happy with this result. And you can see the dot actually also kind of shifted a little bit. But very close to the determinist optimization. So we actually achieved, we think we want to do, because the computer power and also the power formulation. So here is a summary of what's, so going from the right to the left, so we have a starting point. The mass is indicated at about 42.56 kilograms. When we optimize it, it get down to 39.32, it's 8% mass reduction, plus the performance is better. And since the performance is significantly better, the cloud move inside the box is a lot more, but you can see the shape of the cloud has changed. It's spread out because we never asked it to get tightened. There's no such a requirement given. So we are very glad to get that solution in the past, because it's much better than we could have done before. So now we're adding the new requirements in with robustness requirement, and it's kind of try to getting as much as possible. What's surprising here is not just the cloud shape could change and the density could change, is that you can see the mass of the two solutions are almost identical. So to me, these are probably not exact the same solutions, but that means this kind of a multi-dimensional space is very complicated. Existing multiple solutions in there. So if you ask a new requirement, it may navigate it to a complete different solution if it exists. In this case, it sounds like it has a different solution, which has the same mass, but different behaviors. You can see the red dot is close, but not really the same in terms of performances. So what I did is going back and look at the solution, like the table I showed you before, the baseline number. And if you look at the deterministic versus stochastic or robust solution, they are not the same. And they are very different sometimes from the baseline. So in this case, 19 become 30 and become 21. So basically deterministic is a good optimization, but the robustness is equally good, but actually has better performance something else, which we didn't ask for. So this is kind of interesting in that with a powerful tool that we could actually navigate the design much more thoroughly. Otherwise, we wouldn't be able to. So the other thing people ask me is that, hey, with the solution you have, I found actually they cannot find the rules very easily as to why this thing is better. That's because the problem is so complicated. There may be multiple solutions and multiple ways to interpret the same thing. you're getting answers meet the performance for the problem you defined. But there might existing alternatives that beyond the one that you already have. So here is just a quick one look at some analysis, basically min max. These are the performances and the range. I won't go through the detail. Basically, the range obviously has been narrowed. And for these 1, 2, 3, 4, 5 performances, and the mass is almost the same, but the variations has been reduced through this. This is one thing I want to just spend a minute here, is that to understand better in the high dimensional space, it's very hard to visualize because it's more than 3 dimensions, very hard to draw. I have, in this case, 30 dimensions. So what I did is that I draw a straight line between the determinist solution. Let's say determinist solution is at 1, 1, 1. And the optimized solution is a different number, 3 sets of number. So I just draw a line going in the hyperspaces from one to the other. And then ask to print out, because we have response surfaces, what will be the performances going through this line? Is it getting better or worse? And what's in between? So this is what you see actually in this. So you can see these are the 3 or 4 performances. It doesn't really matter what it is. And it's okay here. The reason I plot these 2 plots is this is different scales. And so it's easy to understand. So you can see the left is nominal, the right is the robust. So these are the 4 lines. Let's say this is purple, green, red, and cyan. These are 4 lines. You can see the first 2 performances, the blue and the green, comparing the left to the right. Actually, the original performance for the deterministic is slightly better than the robustness solution. So the robust will make the performance a little worse because, like I said, lower is better. That's easy to remember. Lower is better. But on the other hand, for the red and cyan, the performance is a lot better for the robustness. So basically, it's pick and choose among many different constraints in order to do the joint probability, how to mix, what's the weighting factor for each of these. So hopefully you can find a solution that actually the joint probability is the best. So that is one conclusion. Second thing is that you can see these curves is not one monotonic, it changes directions. So it's likely if you have a optimization, it will get stuck in the local optimum. It doesn't know even there is one that's better or worse over there. So it will tend to actually stay here because the slope sensitivity. And so it's happily converge to a solution and thinking that is the solution. So unless you further explore and going out, you will not be able to find the second solution, which is far away from the first solution. So this is a kind of interesting point that I want to raise up and just kind of food for thought in terms of the optimization. So with this, then we have a much better understanding and have a tool that we can use to solve a lot of different kind of similar problems. So kind of recap is that we have a tool then actually we're able to successfully solve the problem. And I'm just putting this thing out there. And you can see this is the original distribution. After we move it, it changes a lot in shape and sizes. And if we put the requirement for variation studies, the cloud gets a lot smaller. And because of that, we actually solve a problem in high dimension that we probably will be very hard to solve with just engineering judgment and intuitions. But the solution makes sense in the end once we see it. That's usually what we find. Actually, you solve the problem, it started to make sense. If it doesn't make sense, you better be, because sometimes something wrong with the methodology, and that's always the case that we find out. So I think time is limited. I just want to mention that there's other things that could be interesting in the future, is that right now we're solving a continuous problem, maybe some discrete, but some engineering designs are very discrete, like adding member, deleting, or different topology, meaning different connectivities, different scenarios. Where do you put the battery, in the front, in the center? So these are not simple continuous solutions that you can parameterize easily. So I think we need additional capabilities to develop, looking out to basically solve these kind of problems. And I'm listing some of these, and they're also including machine learning and AI, which is the hot topic that we are kind of pursuing, which is outside scope. But if you can generate designs through scenario analysis with machine learning capable methodologies, then you will be able to actually go through even wider variety of design possibilities. So I would just stop right here to see if there's any questions.
Okay, thanks, Simon, for this interesting talk. And we have time for questions. So please feel free to unmute yourself and ask your question, or type the question in the chat and I will read it out. Okay. So the software you are using, is it an in-house developed software, or you are using some open source software, or what kind of tools are you using to run the simulations or optimizations?
Yeah, like I mentioned earlier, we have used many commercial software on the market. There's a pretty capable software out there, but we were not happy with the performance for very large problems. So we developed some in-house capabilities to address it. We're pretty happy with the performance that we have so far. It's still kind of state of art.
Are you using GPUs or CPUs, or are you using hybrid calculations?
Yeah, for the optimization, we are using CPUs, but a lot of massive parallel CPUs that are dedicated for this work. The GPUs, right now we are finding useful for machine learning training ability, but we don't use GPUs for this because I just answer from not expert point of view, is that GPUs probably is good for very massive parallel computation, but simple computations, like a neural network kind of a propagation. But we actually have highly nonlinear physical system, so they run best on CPUs, but we make the CPU parallel together. And the optimization algorithm itself does not take a lot of brain powers. Basically, they are working on the response surfaces, so they can converge pretty quickly. So we actually conduct a lot of optimizations for each iteration between the iterations.
Okay. Do we have more questions for Simon?
Thank you, Simon, for the very informative and interesting talk. I'm very curious about one thing that you mentioned earlier. I think it's in the beginning, towards the beginning, when you talk about the role of design of the car, different components, and the competition between the strength and the energy dissipation. I'm wondering, in the topology optimization or in the optimization design process, will the plasticity be something that could be interesting to consider? For example, large deformation or finite deformation plasticity?
Yeah, so this is a good question. Basically, we're using commercial softwares to evaluate all the plasticities. So we have material properties that from the test lab that look at not only the plasticity, but also strain rate hardening effect, and depending on the speed of the crush. So it's getting pretty complicated in these nonlinear models. So here we are using these nonlinear models and its complexity try to solve an optimization problem.
Right, and would that be considered embedded in the optimization loop, the plasticity, or is more of a analysis that after that you have a basically post-analysis or pre-analysis of the design?
Yeah, so the optimization is outside the analysis itself. So if you have an element formulation and you need to apply loadings on it, and then we will wait until the solver completes its solutions to give us the output in terms of the behavior in simulation. And then we will investigate basically the relationship between the input and output relationship, and then optimize that way. So we skip the middle. That's basically the physics part. But I think there is some ideas that we have that we might be getting into the details, especially with the current machine learning capabilities, because you can imagine right now we are working on an input-out relationship without knowing the true animations or deformations of each of the element and each of the part. So we are losing a lot of information in optimization. Because also observing the engineers, how they do work, they basically look at the animation and say, aha, I can see something going on, so I need to fix something. So the optimization today is not doing that. It's more based on only numbers. It doesn't have the graphics, imaging capability. So one direction I have some ideas that how do we use the computer vision to understand the details of the crush behavior when you have hyperplasticity or plasticity deformations, and using optimization to kind of balancing different structures that way. So we get into the that's how we get into the details of the finite element. Currently, I don't.
Gotcha. Yeah, I'm asking because we're recently working on topology optimization considering plasticity. So I'm very curious on seeing different applications. So it seems that the crashworthiness probably would be one interesting application.
Yeah, this is the holy grail for us. So I do not know what method do you have. We actually, this is different than topology because this is MDO, which is a dumb way to optimize. And topology is looking at the string energy minimization, and we're generating new structures. So in this case, linear low cases has been used for a long time. So we actually have interest in this called ESL method, equivalent static loading method, where we're taking nonlinear loads from the nonlinear simulations and superposing onto each other based on each time steps, and then using that to solve a surrogate model with linear structure. We found that to be somewhat successful in topology optimization. So I do not know what research area do you have. I can talk to you maybe offline.
Sounds great. Sounds great. We'll follow up offline.
Okay, so I think we are a little bit over the 1 hour we planned for this meeting, but let us thank Simon again. It was a really interesting talk, and it's always nice to see what industry is doing from the national lab and academia side. And thanks again for giving your really interesting talk.
Okay, thank you, everyone.